Section 4.1, Introduction to Differential Equations. Woo, exciting. So, differential equations. They're about solving equations that involve derivatives or differentials. Now, what you did in Calc 1 was if you had a function that was like y equals e to the sine x, you would take its first derivative, or dy dx. Alternatively, y prime equals chain rule, cosine x, e to the sine x. This was what we did maybe a semester back in Calc 1. Now, what if you're given something like dy dx equals y cosine x, and now you want to find a function y that makes this a true statement? This is where differential equations come in, because we have to deal with an equation involving derivatives or differentials like dx or dy of one or more dependent variables with respect to one or more independent variables. Now, just a sneak peek for how to solve this. It is a technique called separables, which we will be covering later. We can classify differential equations by their type, order, and linearity. Let's talk about type first. There are two main types of differential equations: ordinary differential equations, or ODEs, and partial differential equations, or PDEs. Now, ordinary differential equations deal with one independent variable only. And these will be what you'll be seeing and practicing in the scope of this Calc 2 course. But for partial differential equations, they deal with two or more independent variables. And you will be seeing PDEs in Calc 3, if you will go on and take that class. So we've covered types, and then this little footnote down here, again, is just saying that you will see partial derivatives being covered in Calc 3. And they treat all variables other than what we are differentiating with respect to as constants. The order of a differential equation is determined by the highest order derivative in the equation. So if we were to look at this example that we've got, we have the second derivative plus 5 dy dx cubed minus 4y equals e to the x. Okay, well, I see 2's here, and I also see a 3 here. But be careful. Power does not mean order. What this is saying is, okay, we have y prime to the third power, but the order is determined by the highest order derivative. So in this case, the order of the differential equation would be 2. And for linearity, we will be covering this in a subsequent section, and that is section 4.5. So let's look at example 1. Determine the order of each of the following differential equations. This would be second order. This would be third order. Again, looking for highest order derivatives. This would be second order. And this would be third order. Now recall for algebra, back in the good old days, when you had something like x plus 2 equals 5, and x equals 3 is supposedly a solution. But to check that it is actually valid, we had to plug it back into the original equation to verify that we get this identity. 5 equals 5. So an algebraic equation is solved by a number, and a differential equation is solved by a function. And when we say a function is a solution of a differential equation, we always say that it's a solution on an interval. And all that means is that the equation works for every x value in some range. The type of interval can be either closed, open, or infinite. But the interval must have no breaks, no jumps, and no holes. Now let's take a look at example 2. Verify that the function y equals e to the 3x minus e to the x over 2 is a solution to the differential equation y prime equals 3y plus e to the x. Okay, so first on the left-hand side, let's find y prime given our y. So you bring the 3 down, 3e to the 3x minus 1/2, it's just a constant, so it comes along for the ride, e to the x. Now, we got this for our y prime, and we're going to plug it back into here. 3 e to the 3x minus 1/2 e to the x is equal to 3. And what was our y? Our y is what we have here in green. E to the 3x minus e to the x over 2 plus e to the x. 3e to the 3x minus 1/2 e to the x. And actually, we don't know if this is equal yet. We want to prove that it is. And we distribute, we get 3e to the 3x minus 3/2 e to the x plus e to the x. And one last step, simplifying it further. Minus 3/2 plus 1 is minus 1/2. That is right. And we see that this is true. What's on the left equals what's on the right. Now it's time to differentiate. We know that f prime of x is just the same as y prime over there. So let's begin. You have y equals x cubed. Its derivative is going to be y prime equals 3x squared. If you have y equals x cubed plus 2, its derivative is weight. Also, y prime equals 3x squared, and that's because this poor constant just goes away. Now, if we have a generalized form where the c is a representation of any constant, its derivative is also, you guessed it, 3x squared. Now, we can see that the derivative is not unique because look at what we just wrote. But in this chapter, we begin over here. Yes, give me a box. And this is what we are now seeking. We are now going to be given the derivative function and asked to find the original function. So, we are given this. We want to find this. So example 4, again, this is just showing that we can have many different particular solutions. For instance, x squared plus 4, x squared plus 2, x squared plus 0, or just x squared minus 2, x squared minus 4, or generalized, x squared plus c, where this c is a constant. We can have all of these different particular solutions to the differential equation, but we have the same derivative. So think, this is the derivative. What function would we have differentiated to get it? That'll be x squared plus c. because we don't know what this C guy is. It could be anything, any number. Now, for initial value problems in differential equations, we are asked to solve a first order ODE, and it's subject to an initial condition. This is generally given as a ordered pair, your initial condition. And what we're really looking for is a particular or specific solution instead of a family solutions that we previously saw. We want a particular C. We don't want a generalized solution. We don't want this family of solutions. We want something that gives us, for instance, that C equals -4 in this case. So that is what a particular solution is all about. So let's look at a fun example. Find the particular solution to the differential equation y prime equals 4x squared that passes through the ordered pair -3, -30. Given that y equals c plus 4x cubed over 3 is a general solution. xy equals -3, -30. And y equals c plus 4/3 x cubed. And we want to solve for c. How do we do that? Literally just plug x and y in, right? Simple. Plug x, y values in and to solve for c. So you have -30 equals c plus 4/3 -3 cubed. And you have -30 equals, well, -3 cubed is going to be -27. So you have, actually what we can do is we can just cancel out the 3's. This turns into a 2. I think that makes our lives easier. So now we'll just have 4 times 9. And you'll have -30 equals c minus 36. You get that c equals 6. So the particular solution that we get for this case is y equals 6 plus 4/3 x cubed. And again, all a particular solution means is to find the c. So let's just write that up. Find what c is. How did they arrive at the general solution? This is where we have to go backwards, because we have our y prime equals 4x squared, or you can write this alternatively as dy over dx equals 4x squared. Now, what we can do is group the dx's together and the dy's together. And when you integrate, you get that y equals 4/3 x cubed plus c. Isn't that neat? Please make a box. It made a box. Awesome. All right, last example of the section. Find the general solution to the differential equation y prime equals 3x plus e to the x. Now, we weren't given an ordered pair like before, right? So there's really no way for us to find a particular solution. So we'll just have to write the plus c at the end. So you have y prime equals 3x plus e to the x, dy dx equals 3x plus e to the x. Moving the dx to the other side, dy equals move dx side 3x plus e to the x times dx. And if you integrate this guy to find your general solution, you get y equals 3/2 x squared plus e to the x plus c. Do not forget that plus c. This is our general solution. Yippee! And we are all done for this section.